So we are starting with the third module in which there are two parts. One is LTI system properties in terms of impulse response, and the other one is Fourier series, continuous time Fourier series. So that we shall deal with later. Fine. So first we shall see this, in which we have system interconnection and properties of systems and step response. So all this we shall see in this particular module. So the first thing that we are seeing here is system interconnection. So everybody just take down this. The first thing that we are learning here is system interconnection. That means you need to have more than one system. Okay, so that we need to interconnect. So when you're interconnecting, you can interconnect the systems in different fashions. Okay, so that is what we are going to see now. Okay, system interconnections. The first type under that is, under system interconnection, is two systems in parallel. If we have two systems in parallel, okay, so what we can do, or how do they look like? Everybody should understand every LTI system is characterized by its impulse response. H of n is the impulse response. Okay, and x of n is the input, and output of LTI system is y of n. Understand? So what is this h of n? H of n is the impulse response. Every LTI system is identified by its impulse response. And if you know the impulse response of the system, okay, then by convolving the impulse response and the input to the system, we can obtain the output. That is where y of n is actually x of n convolution h of n. X of n is the input to the system, and h of n is impulse response of this. What is impulse response? What is impulse response? Impulse response is the response of the system when the, see here, if you have an LTI system, okay, so which can be represented like this, and if you have delta of n as the input, fine, response to delta of n, okay, is impulse response. So this is impulse function. This is unit impulse function. This is unit impulse response. So every LTI system is identified by its impulse response, how it responds to the impulse function. Okay, so that is what is the characteristic of an LTI system. Every LTI system has got unique h of n. So if you know h of n, then by convolving the input with h of n, you will get output. So that is what one needs to understand. So this is the prerequisite. So this is something that one should know. Fine. Now we shall have two such LTI systems in parallel. Understand that? So when we are asked to have two such systems, so we can just represent them like this. So this is one system, okay, this is another system, and I've told you every LTI system has got its own impulse response, right? So let this LTI system has the impulse response h1 of n, and the second system has the impulse response h2 of n. Fine. Now what I'll do is I'll apply the same input to both the LTI systems. See here? So direction is important because it's input. So what is that we're applying? We're applying the same input x of n. Understand that? And output of these two systems are being added. Added means it is being summed up. That's why it is shown as summation. Fine. So this h1 of n plus or minus this, okay, would give you what? Y of n. Okay. So this is the same input to both LTI system 1 and LTI system 2. Okay, let the output of LTI system 1 be y1 of n and output of LTI system 2 be y2 of n. Understand? So what is y of n here? So this is how we have to interconnect the system if we are asked to interconnect them in parallel. Fine, we apply the same input and the output of both the LTI systems are being added. So that means the overall output, therefore, the overall output y of n is given by what? Y1 of n is the output of first system, y2 of n is the output of the second system, and y of n is the output of the overall system, parallel system. Understand that? So this output, overall output would be what? Y1 of n plus or minus the second output, y2 of n. Understand that? Now, every output of an LTI system is what? What is output of an LTI system? See, output of an LTI system is the convolution of the input and the impulse response. Understand that? So, therefore, since we can say, or let's just write here. So, y1 of n can be written as what? X of n convolution h1 of n. Right? Plus or minus x of n again, because it's the same input to both the systems, and convolution sum with h2 of n. So this is how the overall output is going to look like. Now since both these have got the same input, okay, so let's take that input out. Okay, so if you take this input out, our y of n would look like this. So x of n you take out, okay, then in the bracket you'll be left with this. Understand that? See here. So if you have two LTI systems in parallel, then and also if h1 of n is the impulse response of first system and h2 of n is the impulse response of second system, then what is the impulse response of the overall system? See here, seeing this, can you tell me that? Therefore overall impulse response is h1 of n plus or minus h2 of n. So when would this happen? When you have systems in parallel, okay, so this is what is going to happen. Fine. So you will be adding or subtracting the impulse responses. Fine. So this is how the system looks like, the overall system. So if you have the systems in parallel, so you'll add or subtract them depending on this sign. So here plus or minus I've given, right? That's why the plus or minus sign has come. This plus or minus this is what we have done. So if you have two systems in parallel, then we add the impulse responses of these two systems, and that would be the impulse response of the overall system. Understand? So this is what is going to happen if you have two systems in parallel. So this is parallel connection is as good as saying this. Understand? Fine. So let's see the second interconnection now. Fine. Two systems connected in cascade. Cascade means series connection. Okay. So let's say two systems in cascade. Cascade means series. Let's understand that. So it comes one after the other. Fine. So how it is going to look like? So first you will have system 1. First you will have system 1. Okay. In series with this, you will have another system. So if this is the first LTI system, then it will have the impulse response H1 of n, and this is the second LTI system having the impulse response H2 of n. So let the input to the system is x of n, okay, and this goes as the input to the second system. Then this is the overall output. Let the output of the first LTI system be y1 of n. So this is how the series connection or cascade connection is. Understand? In cascade connection, output of the first LTI system is going to be input to the next LTI system. Understand this? Now, what is y1 of n here? Anybody? What is y1 of n? y1 of n is x of n convolution sum h1 of n. What is y of n, the overall output? This is y1 of n convolution sum h2 of n. Understand this? Now let me call this as equation number 1 and this as equation number 2. So equation number 1 is the output of first LTI system, and equation number 2 is the output of second overall. It's not second, you can say second system or overall system. Understand that? So this is how y of n and y1 of n can be represented. Fine. Substitute now. Substitute equation 1 in 2. It implies what? So equation 2, therefore equation 2 will imply what? Y of n would be, okay, y1 of n needs to be substituted from equation 1, so that is x of n convolution h of n. Let's put this in bracket because this is your y1 of n, and this is being convolved with h2 of n. Fine. Since convolution is associative, since convolution is associative, okay, y of n can be written as x of n convolution. Now the bracket I'll shift. First you will obtain the convolution sum of the two impulse responses, and then the result needs to be, this can be done because this is associative. Understand that? Therefore this system now would look like what? That system would now look like this. So if you have two systems in cascade, then the overall impulse response would be this. Fine. So this is what is the meaning of this. This is what is the meaning of having two systems in cascade. Is this okay with you, everybody? Fine. So if you have two systems in cascade, you'll be combining these two as what? What is the combination of these two impulse responses? It is convolution sum of these two. Here, that means this system is as good as this. h1 of n convolution sum h2 of n. Okay, here you have x of n and here you have y of n. So this is as good as this. Similarly, this system is as good as this system. Understand, if you have that in parallel, you are adding them or subtracting them. If you have them in cascade, you'll be what? Convolving the individual impulse response to get the overall impulse response of the system. Is this understood now? Now we shall take one problem on these interconnections. Fine. So let's see this problem. So in this problem, we have been given different LTI systems connected in different fashion. There are some systems connected in series. Okay, there are some systems connected in parallel, and they have given us what is h1 of n, h2 of n, h3 of n, h4 of n. All impulse responses have been given. Fine. So they are asking us to find the overall impulse response of the system. Overall impulse response of the system. Okay, so we need to first simplify this. Okay, if these two are in parallel, so what operation we need to be performing on the impulse responses of these two systems which are connected in parallel? And after that, this parallel system is connected in series with this. So what you should be doing with the impulse responses of these two systems? So all that we have seen now. Okay, if there are systems in series, we have to convolve the impulse responses. If the systems are in parallel, then we need to add or subtract them. Fine. So let's do that now. Fine. In the solution, let's go on what? Combining the impulse responses. Now, everybody just understand, since these two are in parallel, what is the overall impulse response of this system? Anybody? Since the two systems with impulse responses h1 of n and h2 of n are in parallel, what would be the overall impulse response of these two systems?
h1 of n plus h2
yes.
of n.
It is h1 of n plus h2 of n, because they are in parallel. Why it is only plus, not plus or minus?
There's only plus.
There is only plus sign here. Understand that? There is only plus sign. That's why it is h1 of n plus h2 of n. So this is the overall impulse response of these two systems. Fine. Now this system is in series with this. That is h3 of n. Fine. So you have h4 of n. Let's take down this. This is h4 of n. Fine. So you have the same input being applied to these two systems. Fine. And the outputs of these two are being added again. And that will give you your y of n. And these two systems outputs are again being added. There is no minus here. Now, what is the overall impulse response of these two systems in cascade? So we have to convolve the impulse responses of these two systems. So how would that convolution now look like? So it is h1 of n plus h2 of n. Let's put this in bracket. And this impulse response is being convolved with impulse response h3 of n. So this becomes now one system. Okay, so this becomes one system. Now in parallel with this, we have h4 of n, right? So in parallel with this, we have h4 of n. Understand? So since they are in parallel, the same input will be applying and the outputs will be added or summed up. So we need to show arrows here. Otherwise, it's wrong. It's incomplete, rather than saying it's wrong, it's incomplete. So now what you will do with this is what we need to be looking at. Again, you have the parallel connection. Parallel connection means you need to be adding them up. And another thing that you are not supposed to miss is these plus signs. If you don't have these plus signs, you don't know whether you are adding or subtracting. Understand? So therefore, it would be what? So this would be your impulse response. The overall impulse response would be h1 of n plus h2 of n, right? Being convolved with h3 of n. Fine. So this is one system, okay, and this is in parallel with another system whose impulse response is this. So this is what is the overall impulse response now. So now you have to, what you have to do with this, you have to have the values given to these impulse responses. Understand that? So this is your x of n and this is your y of n. Get this point, everybody? Now you need to bring all these. U of h1 of n is this, h2 of n is this. So you need to bring all these into this equation and see what would that happen to be. Everybody get that point? Okay, so let's do it now. Fine. So if it is h1 of n and h2 of, what is h1 of n? h1 of n is u of n, isn't it? So see here, they're writing it as this h1, 2, 3, 4 of n. That means this is overall impulse response. And overall impulse response we have obtained as this. So this is the overall impulse response we have obtained. Let's just rewrite that. Okay, so this will be summed with h4 of n. Now let's go on substituting the values. h1 of n is u of n. And h2 of n is what? U of n plus 2 minus u of n. U of n plus 2 minus u of n. So that is what you have within the bracket. Okay. So this is being convolved with h3 of n. What is h3 of n? h3 of n is given to be delta of n minus 2. Okay. So let's put this as flower brackets. You will have better understanding. So this is one part of it. Fine. So this is what you're seeing. Fine. So this is being added with h4 of n. That is this alpha power n u of n. So this is how it looks like. Now see here, you have u of n and minus u of n, plus u of n and minus u of n you have within this bracket. So these two will vanish, right? So you will be left with what? U of n plus 2 convolution delta of n minus 2, right? Delta of n minus 2. So what is this? What is this? Anybody? So what is this part going to be? One needs to think. Anybody would like to answer that? Which property is this? Shifting property. So we know that x of n convolution delta of n, okay, is what? Is x of n being evaluated n equal to 0, so it is x of 0. Okay, so therefore h1 2 3 4 of n is, what is x of n here? X of n is delta of n plus 2, right? So delta of n plus 2, right? So what we need to do with this? So it is u of n plus 2, okay, with n substituted as what? N minus, this is x of n. Sorry, this I'm writing wrong. See, this is not the convolution property. This is what is the identity properties. Okay, so if you convolve any signal with delta of n, okay, so you will get back the same signal. Understand? So here it is u of n plus 2 is the signal, okay, and but n has to be n minus 2 here, plus alpha power n u of n. Understand? So this is how the signal looks like. Fine. Now see here, if you have x of n being convolved with delta of n, you will get back x of n. Okay, and this is one thing. Or if you have x of n being convolved with delta of n minus n naught, okay, then you will get x of n minus n naught. Everybody understand this point? I think it's better we go on with this property rather than this. It's better we go with this property. This looks suitable here. Saying what is that we're doing? If you are convolving any signal with delta of n minus n naught, you will get that signal, okay, wherein the time axis or the n is being evaluated at n minus n naught, or this is being replaced by n minus n naught. So this is what we do here. This is as good as x of n, right? This is where n is being replaced by n minus n naught. That's it. So here what you will do, this is your x of n. In this x of n would be replaced by n minus 2. That is what is being happening. Understand? So therefore, we can say it is u of n minus 2 plus 2 plus alpha power n u of n. So therefore, the overall impulse response of the system would be given by what? U of n plus alpha power u of n, or you can take u of n common, okay, or you can take u of n common and write your h1 2 3 4. This is the combined, the overall, okay. You can take u of n common and write it as 1 plus alpha power n within the bracket. And this is what is asked. The same can be done for continuous time systems also. So the interconnections that I have shown here, fine, whether it is in parallel or cascade, what I have shown you here is applicable for continuous time systems also. Okay, so we shall take one problem on the continuous time systems. Understand that? So take down this problem number 2, everybody. Problem number 2. Find the response. Find the response y of t of the cascaded system. Find the response y of t of the cascaded system shown in figure. So what is shown here is this. Everybody just copy it down. You have h1 of t. This is continuous time, mind you. So h1 of t you have here. Okay. This is being cascaded with another system. Fine. With the impulse response h2 of t. And the input to the system x of t is given as u of t. Fine. And they are asking us what is y of t. Understand that? Let this be y1 of t, where h1 of t is given by e power minus t u of t. h2 of t is given by e power minus t u of t again. So the same they are given. E power minus t. Both are e power minus t u of t. Understand this point? So if they are in cascade, what would be the impulse response? Anybody in the solution, what we can do? So the overall impulse response h1 2 of t, let's write h1 2 of t, right? Why? Because there are two impulse responses, h1 of t and h2 of t. So those two we are taking overall now, overall impulse responses. Since they are in cascade, okay, it is h1 of t convolution h2 of t. Yes or no? Isn't it? So it's as good as doing this. h12 of t is actually e power minus t u of t being convolved with e power minus t u of t. This is what it is. Understand that? So instead of this, rather let's do this. Everybody just change this. Otherwise, this problem will be again a big problem. Let's you make use of this. Delta of t minus 1. Let's have this as delta of t minus 1. The second what? Because we will understand that property well. So this is being convolved with what? Delta of t minus 1. So what would this be? We know that convolution integral of x of t with delta of n t minus t naught is x of t minus t naught. Therefore, h12 of t would be what? Would be what? E power minus t minus 1. So that needs to be in bracket, mind you, into u of t minus 1. Understand? So if we write this properly, so this would look like what? E power 1 minus t u of t minus 1. So this is the overall impulse response. What they've asked us, What have they asked us? They've asked us to find out the output of the given system. Yes. See, what is that they've asked? Find the response y of t of the cascaded system. So therefore, y of t would be what? So therefore, y of t would be what? X of n being convolved with h12 of t. Sorry, it's not x of n. It's x of, what is that they've given? The input is x of t, right? The input is x of t. And what is that input x of t? See, that is given as u of t. The input x of t is given as u of t. So therefore, y of t would be u of t being convolved with e power 1 minus t u of t minus 1. So this is what is the response of the system given by. Understand? You can further go to obtain what is y of t. Okay. But since it is interconnection of systems we are dealing with, fine, we can just say this. So further you can just see, use the procedure, use the procedure to find out the convolution integral. Okay, so let's not do that here. Let's not do that here. Fine, so let me put the note y of t needs to be found out using convolution integral method. Okay, but since it is not in the scope of what we're learning here, let's stop it there. So we have stopped abruptly, mind you. This is not the end of it. So we have to remove this and see what it is going to be. But the response would be this. The response would be cu of t being convolved with the overall impulse response of the system. So the overall impulse response is obtained to be this if h12 or h2 of t is delta of t minus 1. If it is this, okay, so this is what we end up getting. And once we do this, it is convolution integral problem. Is that okay with you, everybody? So let's see these properties of convolution integral. So we have seen such properties in convolution sum also. What is x of n convolution delta of n? We have seen that also. So on the similar grounds, we shall see what if you are convolving a signal with an impulse function. Okay, so we shall just see this. It will be clear to you because in the problems that we have just solved, you have made use of these properties. See, if you're convolving the signal with delta of t, you'll get back the same signal. So in that sense, delta of t is acting as an identity sequence. Yes, convolving a signal with delta of t will give you the same signal back. So in that sense, this is identity sequence. So delta of t as identity sequence is the first property. Okay, so how we can show you that? Show the proof of that here. So what is convolution integral equation? So it's x of tau into delta of t minus tau. Understand? By impulse function properties of impulse function, unit impulse function. Okay. So it can be given by this integration. We have seen how to evaluate this integral, right? So this evaluation of integral is as good as evaluating this x of tau at tau equal to t. Why at tau equal to t? Because where do you think this tau exists? Anybody? Where do you think this tau exists? So let me just draw that for you. Okay. So what we are seeing is this. Let me just take the whole. I don't think I can be able to. No, I'm not able to copy that. So let me just come here. So what they're saying is this. Fine, in the properties, convolution integral property. What is it? What is being told is this. The first one is the associative, commutative, and distributive. Let's leave that and let's just see what if the impulse functions come. Okay, we are seeing that now. X of t being convolved with delta of t. Okay, it is given as x of t. Okay, so let's go with proof of this. So let's take the LHS, which is x of t convolution delta of t. So it is what? This is tau ranging from minus infinity to plus infinity, x of tau delta of t minus tau, okay, with respect to tau. Now, where do you think this delta of t minus tau is existing? Anybody would like to comment on that? So where is this delta of t minus tau is existing? If you understand that, then we can evaluate this x of tau in association with that. So can anybody tell me where is delta of t minus tau existing? With respect to tau, let me draw. So if this is tau means, where do you think delta of t minus tau existing? Anybody? Or just work it out and see. Delta of t minus tau. It's a single strand. Okay, that means it's what is delta of t? Delta of t is this. Let me write this here. This is delta of t, which is infinity at t equal to 0. So that means delta of tau is what? Delta of tau, it's not t, mind you, because we are sketching it with respect to tau, right? So it is delta of tau, and this is 1 and this is 0. Understand this point? Now, if this is delta of tau, can you tell me what is delta of minus tau? Delta of minus tau would also be the same, because it is existing only at where? Tau equal to 0. So in that sense, this impulse function is which signal? We have done the classification, right? Initially. So seeing those classification, can you tell me delta of tau is equal to delta of minus tau? So that means this impulse function is an even signal. Okay. Now, if this is delta of minus tau, what is delta of t minus tau? Anybody? The delta of t minus tau is shifting this delta of minus tau to the right by t seconds. So if it is at 0, delta of t minus tau would be at tau equal to t. Understand this point? Okay. So we shall see now. Since delta of t minus tau is existing at tau equal to t, okay, x of t convolution delta of t would be, okay, given as x of tau being evaluated at tau equal to t, because this exists at tau equal to t. So this also should be evaluated at tau equal to t. So in that sense, this is x of t, which is equal to your RHS. So if you convolve x of t with delta of t, you will get back the same. Okay, so this is the proof to that. This is how we prove that. Is that understood? So similarly, see the second one here. This is understood, right? Why this is existing, this delta of t minus tau is existing at where? At t equal to tau. This exists at t equal to tau. Since this exists at t equal to tau, we need to evaluate this x of tau at tau equal to t. So it is x of t. So second signal, where is delta of t minus tau existing? Here, this. So shall we work out that? So what is it saying? Second property. If you have x of t being convolved with delta of t minus t naught, then it is x of t minus t naught they are saying. Fine. So let's see the proof. Fine. So let's take LHS, and this is x of t convolution delta of t minus t naught. Fine. So if we have the equation for this, how does it look like? So integration tau ranging from minus infinity to plus infinity, x of tau into delta of t minus tau minus t naught is how it looks like. Understand that? So this is d tau. So let's write it in a proper form. So this further can be written as tau ranging from minus infinity to plus infinity, x of tau delta of, see here, t minus t naught we shall write in the bracket, then we shall write minus tau d tau. Now see here, if delta of t minus tau exists at, if delta of t minus tau exists at tau equal to t, then this exists at where? Anybody? Exists at tau equal to t minus t naught. Okay, so therefore we have x of tau being evaluated at tau equal to t minus t naught. So we get it as x of t minus t naught, which is your RHS. Is understood? So why I'm taking this is because we have considered these properties to solve the problems that we had taken in system interconnections. Understand? So what is the third property telling you here? If you're convolving, see here, it's all convolution of a signal with impulse functions and shifted impulse functions. Now suddenly you have the x of t, a signal being convolved with unit step function. Okay, so what is it told here? If you they're just telling us that, see, if you convolve your signal with u of t, then it is this. So how to prove this is what we're looking at now. Okay, so let's take that. So let's take this x of t being convolved with, right? The third one is x of t being convolved with u of t. Then it is integration tau ranging from minus infinity to t. Yeah, minus infinity to t, x of tau d tau. So this is what we need to prove, the third property. So let's take the proof now. Let's take LHS, which is convolution of x of t and u of t. So according to the equation, we have tau ranging from infinity to plus minus infinity plus infinity, okay, x of tau u of t minus tau d tau. Now we need to analyze u of t minus tau. So this is your job now. What is u of t minus tau? What is this? So if you understand this, then the things will fall in place. Understand? So let's see that. So mind you, once it is within this integration, it is all with respect to tau. Understand? So just see here, for the curiosity, I'll write if this is tau, and if this is 1 and this is, sorry, if this is 0 and this is 1, can you tell me what is this? What is this signal? Please respond.
U of tau.
This is u of tau. It's not u of t, but it's u of tau. Good. Why? Because x-axis is tau. Now to obtain this, what do we need to perform on this? We need to take the reflection of the signal. We need to take the reflection of the signal, that is u of minus tau. Fine. So how the reflection of the signal should look like now? See here. The reflection of the signal is this. So this is 1, this is 0. This is u of minus tau. Now what you will do? You will obtain u of t minus tau. Can you tell me what is u of t minus tau now? The range of u of tau is 0 to infinity. Range of u of minus tau is minus infinity to 0. So what is the range of u of t minus tau? Yeah. Answer please. What are we doing on u of minus tau? We are adding t to this minus tau, right? So we are adding t to a reflected signal. So if you add anything to the reflected signal, that reflected signal should move to the right. So in that sense, okay, so this signal is as good as this. So this is from minus infinity to t. Everybody understand? So this is what one should understand here. You need not have to do all these exercise. So what is this? U of t minus 2, t minus tau is 1, okay, for tau ranging from minus infinity to t. Fine. So this is 1 from where to where? This is 1 from minus infinity to t. So beyond t, what is this? Beyond t. For tau greater than t, what it is? 0. This is 0 for tau greater than t, and it is 1 for tau minus infinity to t. So that is what we need to understand here. Okay, so let's just push this to right somewhere. This is just an exercise that I just demonstrated. Fine. So this is not important. So let's keep it aside. Fine. So here we need to just say this. Okay, what is that? U of t minus tau is equal to 1, okay, for tau ranging from minus infinity to t, and it is 0 for tau greater than t. This is what one should understand. So therefore this looks like what? Therefore x of t convolution u of t would be, see here, see the integration now. It is tau ranging from minus infinity to t, okay, x of tau. And what is this u of t minus tau in this duration? From minus infinity to t, see here, from minus infinity to t, this u of t minus tau is 1. So this is 1. So that's why they write 1 here, and this is d tau. Okay, so that is what they have asked us to what? Prove. Fine. So it is tau ranging from minus infinity to t x of tau d tau. So this is your RHS. So everybody understand this? So these are the properties that we had used in the problems that we have solved. Okay, let me just take you there. See here. Where is that? No, it's not. Yeah, it's here. See here, a signal is being convolved with the shifted unit impulse response. So which property we're using? This is the property we're using. That's why. How does this look like? It looks like this. This t would be t minus 1. So that property is used. And here in the previous problem also, though it is discrete time, we have used that property. See here, same property. In discrete time also it holds good. Get this point? Okay, so that's why I took that proofs of the properties where the delta of t is involved.